Hello everyone and welcome to Linear Algebra Tutorials. Beside linear algebra tutorials, on my YouTube channel you can find a large number of tutorials covering different topics such as robotics, control systems, and machine learning. In this linear algebra tutorial, we will learn how to calculate eigenvalues and eigenvectors of matrices by hand. It is true that today almost all calculations are done by using computers. However, knowing how to calculate a linear algebra object or a quantity by hand is very important, since only in that way we can truly obtain a long-lasting and solid understanding of numerical linear algebra. Moreover, by learning how to compute quantities by hand, we will obtain enough insights into how linear algebra algorithms work behind the scenes. This knowledge will enable us to develop new algorithms. Here's a brief outline of this video tutorial. First, we will go over the definitions of eigenvalues, eigenvectors, and characteristic polynomial. Then, we will do an example. We will compute eigenvalues and eigenvectors of a 3 by 3 matrix shown over here. We will present a detailed procedure for computing eigenvalues and eigenvectors, and we will present all the steps. But before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as more than 350 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Also, if you have some questions or a comment about the material presented in this lecture, please feel free to ask your question in the comment section below. Okay, let's start. We start with the definition of eigenvalues, eigenvectors, and characteristic polynomial. Let us assume that we are given an n by n matrix A. Then, a complex number, lambda, is an eigenvalue of the matrix A if there exists a non-zero vector v such that this equation is satisfied. The vector v is called the eigenvector of the matrix A. Let us write this equation once more. We have A multiplied by the vector v should be equal to lambda times v. Over here, v is the eigenvector and lambda is the eigenvalue. Lambda can be complex number as well as the entries of the eigenvector. Now let us consider this equation. A times the vector x. Here x is an arbitrary n-dimensional vector. That is, x is Rn. Or better to say, x is in Rn. We can say that the matrix A acts on the vector x. This means the following. Depending on the vector x, the matrix A can rotate and scale the vector x. For example, if this is our original vector x, and if we multiply this vector by the matrix A, we can obtain some other vector. For example, vector given over here, where this vector is A times x. To remind you, A is n by n matrix, so the dimensions will not change. Depending on the direction of the vector x, the matrix A can rotate and scale the vector. Now, if the eigenvalue is real, then the eigenvector can be interpreted like this. Let us assume that this vector is the eigenvector of the matrix A. This vector satisfies this equation. A times v should be equal to lambda, where lambda is the eigenvalue, times v. Over here, for simplicity, I assume that lambda is a real scalar. How can we graphically and geometrically interpret this multiplication? The eigenvector is the vector that is only being scaled by the action of the matrix with the possibility of change of the sign. And we can see it from this equation. If the matrix A acts on the vector V, we are obtaining this vector lambda times V. That is, we are obtaining the vector that is a scaled version of V. And here it is. This is lambda times V. Of course, we can change the sign. For example, lambda times V can be in this direction. If lambda is negative, of course. Now that we understand the concept of the eigenvector, let us explain how to compute the eigenvectors and eigenvalues. Our original equation can be written like this. What did we do over here? The equation that defines the eigenvectors and eigenvalues looks like this. A times V is equal to lambda times V. From this equation, we obviously obtain A minus lambda times identity matrix multiplying V is equal to 0. From this equation, we can see that the eigenvector is actually in the null space of this matrix, A minus lambda I. The process of computing the eigenvector V is equivalent to the process of searching for non-zero solution V of this homogeneous system of equations. That is, we are searching only for non-trivial solutions. This system will have a non-zero solution V if and only if the determinant of the matrix A minus lambda I is equal to 0. That is, the system has non-trivial solutions if and only if this equation is satisfied. This equation is actually a polynomial in lambda. This equation is called the characteristic polynomial or the characteristic equation of the matrix A. The solution of the characteristic polynomial, or equivalently, its roots, are the eigenvalues of the matrix A. Generally speaking, this polynomial is of order n, and consequently we will have n eigenvalues. Note here that some eigenvalues can be identical. Let the eigenvalues be denoted by lambda 1, lambda 2, lambda 3, and lambda n. Let us for simplicity assume that the eigenvalues are distinct. That is, to every eigenvalue we can associate an eigenvector. Let such eigenvectors be denoted by v1, v2, and vn. Once the eigenvalues are computed by computing the roots of this polynomial, the eigenvectors are determined by solving this system of linear equations. So what do we do over here? Let us assume that we computed lambda 1. Then we simply form a system of linear equations that looks like this. A minus lambda 1 times the identity matrix multiplying v1 should be equal to 0. And over here, we want to solve the system of equations for v1. And in that manner, we will compute the eigenvector. We repeat this process for all n eigenvalues. That is, we need to solve n systems of equations to compute the corresponding eigenvectors. Okay, that was the definition. Let us now solve a numerical problem. That is, let's compute eigenvectors and eigenvalues of a 3 by 3 matrix shown over here. The eigenvalues are given as the roots of the characteristic polynomial. And let's form the characteristic polynomial. Here is the characteristic polynomial, and first we substitute this matrix over here. Then we substitute the identity matrix, and finally we obtain this expression. If we compute this expression inside, we obtain this problem. That is, we need to compute the determinant of this matrix. And here you can see eigenvalues. How to compute the determinant of this matrix? We can expand the determinant expression by using these coefficients. We use these coefficients since we see 0 over here, and consequently the corresponding term will be equal to 0 and the expression will be simplified significantly. So let's do that. Okay, so let's start with this coefficient. What do? We erase this column, we erase this row, and we compute the determinant of this submatrix. And here it is. Over here, you should keep in mind that the sign in front of this term is +1. Signs are very important. So we have 6 multiplying -2, and this expression over here simplifies to this. Okay, so that was the first coefficient. Then, over here, we have 0, right? If we didn't have 0, we will have to multiply the entries of this submatrix to compute the corresponding term. However, since we have 0, the expression is 0. And finally, we have the third coefficient given over here. We erase this column and this row, and we compute the determinant of this submatrix over here. And here's the result. From this expression, we obtain this expression. And we can rearrange this expression to obtain our final characteristic polynomial over here. From this characteristic polynomial, we can see that the eigenvalues are lambda1 is equal to 0, lambda2 is equal to -4, and lambda3 is equal to 3. We obtain lambda2 and lambda3 by simply computing the roots of the quadratic equation. Lambda squared plus lambda minus 12 is equal to 0. And you can double check and you can see that these are the zeros of this quadratic function. Next, we need to compute the first eigenvector. To compute the first eigenvector, we will take the first eigenvalue and we will go back to this equation. We will substitute lambda1 over here and we will solve for v1. Let's do that. Here is the equation. We substitute lambda1, that's equal to 0, and we obtain this expression. If we substitute the matrix A in this expression, we obtain this expression. Now, let the components of the vector v1 be given like this: v11, v12, v13. Then, by using this expansion, we can write the system of equations like this. And if we multiply this matrix by this vector, we obtain the expanded system of equations. Here it is. And we need to solve the system of equations for v11, v12, and v13. We will solve this system of equations by using the Gaussian elimination. First, we multiply the first equation by -6, and we add the result to the second equation. And consequently, we will obtain this equation. Then, we add the first equation to the third equation. That is, we add this equation to this equation, and finally, we obtain this equation. What do we see over here? 0, 0, and 0. And this equation can drop out. Now, from the second equation, that is from this equation, we obtain that v13 is minus 13 over 6 multiplying v12. This is a very important result. By substituting this equation into the first equation over here, we obtain the expression for v11, and v11 becomes 1 over 6 multiplying v12. Now, let us analyze the equation 16 and the equation 17. From the equation 16, we can see that v13 is a function of v12, and similarly v11 is a function of v12. However, how to choose v12? Well, we have a complete freedom to choose v12. That is, the original system of equations has an infinite number of solutions. And we have a freedom to choose v12 in order to fix the solution. And this is often the case when one tries to compute eigenvectors and eigenvalues of matrices. Now let us substitute the expression for v13 and the expression for v11 in the general expression for the eigenvector v1. And as the result, we obtain this vector parameterized by the scalar v12. We have complete freedom to select the scalar v12. For example, we can select the scalar as 12. As the result, we obtain the following eigenvector. Here it is. By selecting any other value of v12, we will also obtain another eigenvector. That is, if we multiply an eigenvector by a constant scalar, the result is also an eigenvector. And this is a very important observation. Next, let's compute the second eigenvector v2. We do that by following the same procedure. We form the system of equations and we substitute lambda 2. Lambda 2 is equal to minus 4 and the expression has this form. Then we substitute the matrix A, identity matrix, and we obtain this expression. Next, let's parameterize the vector v2. We can express the vector v2 like this. By combining this expression and this expression, we finally obtain this system of equations. And this system of equations can be expanded. Let's solve this system of equations. Now, first, we will multiply this equation by minus 1 and we will place this equation at the top. As the result, we obtain this system. That's equivalent to the original system. Next, let us multiply the first equation with minus 5 and let's add the result to the second equation. As the result, we obtain this equation. Then, let us multiply the first equation by minus 6 and let us add the result to the third equation. And as the result, we obtain this equation. Okay, we proceed. By multiplying the second equation with minus 9 over 8, that is, by multiplying this equation from any side by minus 9 over 8, and by adding the result to the equation number 3, that is to this equation, we obtain this system. The third equation again is completely zero. It carries no information. However, the second equation is important. From the second equation, we can conclude that v23 is 1 over 2 v22. Now let's substitute this equation in the first equation, and as the result, we obtain that v21 is minus 1 over 2 v22. By using this equation and this equation, and by going back into the expression for v2, we again obtain a parameterized eigenvector. Here it is. Again, we have a complete freedom to select v22. Let's select v22 to be equal to 4, and finally we obtain the second eigenvector. Here it is. Finally, let us compute the third eigenvector. We do that by following the same procedure. Again, we form the system of equations, then we substitute lambda 3. To remind you, lambda 3 is equal to 3. Here is the expression, and after substituting the identity matrix over here, we obtain this expression over here. Next, let us parameterize the eigenvector. Here is the parameterization. By combining this equation and this equation, we obtain the system of equations. Here it is. Next, let us multiply the third equation by minus 1 and let's place this third equation at the top of the system. As the result, we obtain this equivalent system. Next, let us multiply the first equation by 2 and let's add the result to the second equation. As the result, we obtain this equation. Next, let us multiply the first equation by minus 6 and let's add the result to the third equation. And as the result, we obtain this equation. Next, let us multiply the second equation by 16 over 6 and let's add the result to the third equation. And finally, we eliminated the third equation. We are only left with the second equation and the first one. From the second equation, we obtain that v33 is minus 2 over 3 v32. Again, let's substitute this expression in the first equation, and as the result, we obtain that v31 is 2 over 3 v32. Again, here is our parametrized eigenvector. We can see that this vector is parameterized by the scalar v32, and we have a complete freedom to choose v32. Let's select v32 as 6, and finally we obtain the final expression for the third eigenvector. Here it is. If you do this procedure by yourself and independently, and I strongly suggest you to do that, it will take you probably around half an hour to do these computations. Okay, that would be all for today. I hope that you liked this video. If you like the videos I create, please press the like and subscribe buttons. Thanks a lot and have a nice day.